The Webb looks so far out that it's capturing light that's been travelling for over 13 billion years. But the universe has been expanding, and so the light has been stretching. And so for the most distant galaxies, we're looking back in time almost to the Big Bang.
The vastness of space is mesmerizing. When we gaze into the depths of the cosmos, we're actually glimpsing light that has journeyed for over 13 billion years. But here's the incredible part. As the universe expands, this light gets stretched along with it. So, when we peer at the most remote galaxies, we're essentially peering back in time, almost to the very moment of the Big Bang. The Big Bang theory is like the cornerstone of modern cosmology. It boldly declares that our universe had a beginning and has a finite age. Yet, since its inception, some have questioned this idea. They've raised doubts about whether the universe really had a singular cosmic birth followed by billions of years of expansion. Back in the 1960s, many of these doubts were put to rest with the discovery of something called the cosmic microwave background. It's like a lingering echo from the universe's early hot phase, and its presence helps solidify the Big Bang theory. However, skepticism has persisted over time, and lately, it's gained renewed attention thanks to some groundbreaking revelations from the James Webb Space Telescope. In a remarkable observation from the early universe, NASA's James Webb Space Telescope, JWST, often hailed as our cosmic time machine, has made a breathtaking discovery. With its ability to capture light that's been traveling for over 13 billion years, the JWST, as explained by renowned physicist Brian Cox, has spotted an immense gathering of galaxies at the farthest reaches of our observable universe. This finding has thrown a curveball at the accepted Big Bang theory. So, the big question arises: should we now reconsider our entire understanding of the cosmos and our place within it? Let's delve into this intriguing notion. Unlike its predecessor, the Hubble Space Telescope, which couldn't detect this ancient light, the JWST has peered deep into the past to witness the formation of some of the very first galaxies. It's like a time machine, allowing us to glimpse moments very close to the universe's birth. This is crucial because the formation of those initial galaxies remains a mystery to us. The light we're seeing has been stretched so much by the universe's expansion that it's now in the form of microwaves. But there's a limitation. In the universe's infancy, it was so hot and dense that light couldn't travel through it, rendering it opaque. This means we can't use light to peer back any further than that early period. However, there's hope on the horizon. While current technology isn't quite up to the task, advancements in detecting phenomena like colliding black holes suggest that we may eventually probe even closer to the Big Bang itself. Whether the Big Bang marks the true origin of time is another fascinating question to ponder. The concept of the Big Bang has its roots in the 1920s and 1930s. Scientists noticed something intriguing when they looked at galaxies far away. The farther they were, the faster they appeared to be moving away from us. This observation, in line with Albert Einstein's theory of general relativity, suggested that a static universe would be unstable. It would either have to collapse or expand if Einstein's laws held true. The fact that galaxies seem to be receding taught us that the universe is actually expanding. As time goes on, things move farther apart, indicating they were once closer together. As the universe expands, not only do distances increase, but light wavelengths also stretch out over time. Since shorter wavelengths correspond to higher energy, this stretching suggests that the universe was hotter in the past and has been cooling down over time. If we rewind this expansion far enough, we reach a point where the universe was so hot that neutral atoms couldn't even form. According to this idea, we should still be able to detect a faint glow of leftover radiation in all directions today, cooled down to just a few degrees above absolute zero. The groundbreaking discovery of the cosmic microwave background in 1964 by Arno Penzias and Bob Wilson was a momentous confirmation of the Big Bang theory. It's like peering back in time to when the universe was incredibly hot, dense, and compact. Essentially, it's glimpsing the very light from the universe's birth. Imagine tuning an old FM radio between stations and hearing that static noise. Well, about 0.5% of that noise is actually echoes of the Big Bang itself. That's how significant this discovery is. As we trace back further in time, we hit a period where it was so blisteringly hot that atomic nuclei couldn't even form. The radiation was so intense that it could tear apart any particles bound together. As we go even further back, protons and neutrons break down into an exotic state called quark-gluon plasma, where densities surpass even those found in atomic nuclei. Eventually, we reach a point where density and temperature become infinite, a singularity where all matter and energy converge into a single, unimaginably dense point. This singularity isn't just a theoretical concept. It's where the laws of physics as we know them break down. It's the origin of space and time itself, encapsulated in the foundational idea of the Big Bang. Every part of this journey, except for the ultimate singularity, has been validated. Scientists have managed to create quark-gluon plasma in labs, generate matter-antimatter pairs, and conduct calculations that align precisely with the predictions of the Big Bang, confirmed through measurements of elements from the early universe and their abundances. Progressing forward, observations have expanded to include the study of fluctuations in the cosmic microwave background, offering valuable insights into how gravitationally bound structures like stars and galaxies form and evolve. Despite the impressive harmony between the Big Bang theory and observational data, the universe as we see it presents certain puzzles that the Big Bang alone doesn't completely solve. If everything indeed originated from a single point within a finite time frame, one might expect to see variations in temperature across different regions of space, given that these regions wouldn't have had time to interact and exchange particles, radiation, or information. Additionally, traces from the universe's earliest, hottest moments, such as magnetic monopoles and topological defects, and some degree of spatial curvature, should still be detectable. However, a Big Bang stemming from a singularity lacks a mechanism to balance the initial expansion rate with the total density of matter and energy. Contrary to these expectations, the universe maintains a consistent temperature across all regions, lacks relics from high-energy states, and displays perfect spatial flatness in every direction. This presents two possibilities. Either the universe inexplicably possessed these properties from its very beginning, or there exists a scientific explanation, a mechanism that orchestrated the emergence of the universe with these specific characteristics. Pradhanatarajan, a theoretical astrophysicist at D University, stresses that while current data hasn't completely upended our understanding of the universe, it does reveal intriguing discrepancies on various scales. Resolving these discrepancies will require researchers to revisit their fundamental assumptions about galactic evolution, possibly leading to the introduction of new ideas while discarding others. It's worth noting that the discovery of these early galaxies is not a recent development. In May 2009, astronauts installed one of Hubble's most vital instruments, the Wide Field Camera, WWFC-3, significantly enhancing the telescope's ability to observe in the infrared spectrum. As the universe expands, light traveling through space becomes stretched into longer wavelengths, primarily in the infrared range. This enables us to see the oldest objects in the universe, which would otherwise be invisible at shorter ultraviolet or visible wavelengths. With WFC-3, Hubble was able to capture light from remarkable objects like the galaxy GN's 11, which existed when the universe was a mere 3% of its current age, approximately 400 million years old. However, Hubble's exploration of this early era was limited, as its instruments struggled to detect visible, bright galaxies, preventing astronomers from fully observing the earliest stages of galaxy formation. When the James Webb Space Telescope, JWST, was launched in December 2021, scientists quickly discarded the notion that there were no galaxies within the first 500 million years after the Big Bang. The discovery of the galaxy Glass Z12, which is approximately 50 million years older than GN's 11, along with subsequent JWST observations revealing numerous galaxies potentially as early as 180 million years after the Big Bang, contradicted this earlier belief. Jan Bay, an astrophysicist at the Rochester Institute of Technology, highlights the surprise among researchers at the abundance of bright galaxies detected by the JWST and their unexpected ease of identification. Moreover, these galaxies may be more massive than previously thought. In the initial period after the Big Bang, extreme conditions facilitated the settling and condensation of matter into structures such as stars and galaxies. As the universe expanded and cooled, conventional cosmological theories suggest that dark matter particles, outweighing normal matter by about 6 to 1, congregated under gravity's influence to form massive halos. Regular matter then gravitationally clustered within these halos, eventually giving rise to the stars and galaxies observed today. According to common models, a galaxy comparable in size to our Milky Way wouldn't have formed until approximately 1 to 2 billion years after the Big Bang. However, the first image captured by JWST of the SMACS 0 723 cluster challenged these expectations. Astrophysicist Erica Jun Nelson of the University of Colorado Boulder identified sizable red disks indicative of extremely massive galaxies undergoing rapid star formation. These 6 dusty elongated galaxies appear to have existed within the initial 500 to 700 million years of cosmic history. Based on their observed brightness, Nelson's team estimated that each of these objects could weigh at least 100 billion times the mass of the Sun, with one colossal galaxy potentially housing 100 billion suns, comparable to our own galaxy. This massive galaxy might even have 2 nearby companions, suggesting its involvement in a galactic group and posing a challenge to existing cosmological models. However, according to M. Kin, a theoretical astrophysicist at the University of Texas at Austin, skepticism remains. Some astronomers propose that the properties of these galaxies might indicate they're predominantly filled with young, low-mass stars, making them roughly 100,000 times less massive than initially estimated. Despite thorough exploration of this possibility by Nelson and her team, they ultimately dismissed it, considering it reliant on too many unlikely assumptions. Another paper from the Cosmic Evolution Early Release Science Program, a prominent JWST survey team, put forth an alternative interpretation for the largest galaxy. They suggested that it may be located much closer to us, appearing over 1 billion years after the Big Bang. By applying certain assumptions to the data, they proposed that some of its light might originate from a supermassive black hole at its center, resulting in fewer stars and an overall mass approximately 10 times lower. Nelson concedes that this perspective is likely correct. The challenges in early JWST research are highlighted by the discrepancies that have emerged. Many of the telescope's initial findings are based on imaging data, where a galaxy's distance and mass are inferred from its brightness and color, a method that is valuable but constrained by specific assumptions. For a more comprehensive understanding of an object's properties, as well as its chronological and spatial context in cosmic history, astronomers often turn to spectroscopy, a meticulous process that breaks down light into its constituent colors, revealing distinct chemical signatures. The cosmic expansion gradually stretches these signatures toward longer wavelengths, providing an accurate measure of the distance traveled by light. An instructive example is illustrated by JWST imaging data initially placing a galaxy called Sears 93316 at 240 million years after the Big Bang, initially marking it as one of the most distant objects ever recorded. However, subsequent spectroscopic measurements contradicted this, revealing a much closer proximity and a less groundbreaking epoch, approximately 1.2 billion years after the Big Bang. Despite encountering such challenges, certain instances have demonstrated the alignment between imaging data and spectroscopy, particularly in the JWST Advanced Deep Extragalactic Survey, JADES. 4 distant galaxies initially identified were confirmed to be at their extreme distances through spectroscopy, notably JADE's GSZ 130, currently holding the distance record at roughly 320 million years after the Big Bang. With the telescope's upcoming observation cycle commencing in July, its spectrograph is poised to gather data on numerous objects, potentially including massive and distant galaxies studied by Nelson and her colleagues. The discovery of prominent galaxies by JWST is prompting theorists to re-evaluate fundamental concepts. Current cosmological models predict the expected number of dark matter halos of various sizes across different epochs in the universe's history. Alice Shapley, an astronomer at the University of California, Los Angeles, highlights a discrepancy, suggesting, if we assume galaxies only reside within these concentrations of dark matter, there aren't enough dark matter halos to accommodate the reported galaxies. Consequently, computer simulations that produce insufficient dark matter, halos and galaxies are losing credibility, and additional data may necessitate further adjustments. Astronomers at the University of Missouri in Columbia recognize that while there is still some flexibility regarding the exact characteristics of galaxies, such as their number, masses, and formation times, this flexibility is gradually diminishing. Many in the field acknowledge that their understanding of galaxy formation may need to evolve in response to observations made by the JWST. The extent of this adjustment remains uncertain. It could be a minor refinement or a more significant overhaul. One plausible scenario suggests that the earliest stars and galaxies may have formed more efficiently than previously thought. It's conceivable that in the early universe, conditions were denser and more compact, potentially facilitating the rapid collapse of gas and dust into stars. Bone and Kolchin propose, perhaps in the very early systems, everything is happening rapidly with no hindrances. Another potential adaptation involves considering a scenario where a significant number of galaxies form much earlier in cosmic history than current theories suggest. This adjustment would imply a higher efficiency of galaxy formation compared to what existing models assume. Alternatively, a more unconventional explanation involves re-evaluating the nature of dark energy, which is typically attributed to the observed accelerated expansion of the universe. While physicists traditionally regard dark energy density as constant since the Big Bang, conflicting measurements of cosmic expansion may prompt a reconsideration of this assumption. Investigations of the nearby universe indicate a faster expansion rate than what is inferred from observations of the early universe. Models predating the JWST, known as early dark energy models, propose a higher quantity of dark energy around 50,000 years after the Big Bang. These models, which aim to address the discrepancy in the expansion rate, also predict accelerated and more abundant galaxy growth in the early universe, aligning with observations from the JWST. However, a significant challenge arises. The standard cosmological model, which features constant dark energy density, has been highly successful in explaining the evolution of large-scale structures, including galaxies, galactic clusters, and superclusters. Any modifications must retain these successful aspects while accommodating the new observations. While many researchers are approaching the new observational tool with caution, refraining from abandoning established ideas in favor of new cosmic perspectives, its introduction has injected fresh energy into the field of astronomy, prompting a thorough examination of foundational assumptions. As Shapley puts it, there are moments in one's career when you realize it's a watershed moment, and the field is currently undergoing one of those transformative phases. Now the question arises, if the Big Bang Theory is just a theory, are there alternative hypothetical explanations for the origin of the universe? The answer is yes, and here are 4 intriguing alternatives to consider. 1. Quasi-steady state theory. This theory directly opposes the Big Bang Theory by suggesting that the universe has always existed with a uniform density and without a beginning. It evolved into the quasi-steady state theory, proposing that as the universe expands, packets of matter are continuously generated to maintain density. However, this theory failed to gain widespread acceptance among scientists, as data from the cosmic microwave background indicated a significant explosion around 14 billion years ago, marking the beginning of the universe. 2. Mirror universe theory. The mirror universe theory presents a highly speculative yet captivating alternative to the Big Bang theory. It suggests that during the Big Bang, two universes were created, one progressing forward in time and the other moving backward in time. This implies that while our universe unfolds from birth to death, the mirror universe experiences a reverse progression from death to birth. An analogy to grasp this concept can be found in the movie Tenet, where objects experience reversed entropy, causing them to move backward in time. Digital simulation. In the 21st century, advancements in technology have empowered humans to create and manipulate simulations of various physical phenomena using sophisticated computers. As technology advances further, there's potential to expand this realm, allowing humans to simulate entire universes with meticulously controlled initial and final conditions. This concept prompts contemplation about the nature of our reality. What if our universe is merely a simulation crafted by a highly intelligent civilization determining our destinies? This notion resonates with the theory of predeterminism, which finds support in phenomena like quantum entanglement, where information seemingly travels faster than light, challenging the principles of relativity. The notion that our universe might have been predetermined from its inception is indeed thought-provoking. Multiverse theory. The multiverse theory posits the existence of an infinite number of universes spawned by fluctuations in dark energy, resulting in multiple explosive events resembling Big Bangs. Many of these universes born from such eruptions may collapse to form black holes, while others, like ours, undergo an explosive expansion that continues indefinitely. This expansion persists until matter is sufficiently dispersed, creating a domain of dark energy where the cycle of Big Bangs repeats, continually birthing new universes. In addition to these alternative theories, there are other intriguing hypotheses such as inflation theory, infinite universe theory, gravity rainbow, and more. While these theories boast logical foundations, none has surpassed the widely accepted Big Bang theory, which, despite its recognition, remains incompletely proven and understood. The origin of the universe remains an enigma, leaving humanity grappling with unanswered questions. If you enjoyed today's episode, please show your support by giving us a thumbs up and leaving a comment to share your thoughts. Your feedback motivates us to deliver quality content and strive for continuous improvement. Thank you for watching, and we look forward to seeing you next time.